Okay, hello everyone.
Hello.
Hello.
Okay, so today we are going to talk about the partial correlation. So until this time, we assume that we only have the two variables. However, we may have one more variable. We may have more than the two variables in the real practice. So here, so we assume that we have many variables, but for simplicity, we assume that we have the three variables, x and y and z, and then we would like to find the correlation excuse me, the correlation between x and y, and then by controlling effect of the z. So here x and y and z, they are the continuous variables, continuous random variables. And then, so we can think about there as a correlation between x and y and z, and x and z. So here, but our main interest is the correlation between x and y. But here, the one thing that we need to be careful is that since z is also correlated with x and y, so this variable z affects the correlation between x and y. So here now our question is so we would like to get the correlation between x and y by the controlling effect of z. Here the controlling means that we would like to um, um, control the effect of we would like to remove the effect of z on correlation x and y, or we can say that in more general, we can say that we would like to think about correlation x and y given the z and here. So to talk about this correlation when we have three variables, now I would like to start to talk about the vector and then the covariance matrix. Basically, we can take care of the general setting when we have many variables. It can also cover the simple correlation case, which is the situation that when we have two variables. So let's the x1 to the x2p be random variables. There's no assumption on this random variables. They don't have to be IID. They don't have to be independent. Just we assume that they are random variables. Then we define the random vector, which is the vectorized version of the random variables. And so I would like to use this bold symbol axis on the x1 through the xp. So which is the so this bold axis, the excuse me, the vectorized version of the x1 through xp. Now we define a mean vector. So which is we take expectation on this vector x, which is the expectation of x1 through expectation xp, which is equal to, I'll say, mu1 through mu_p. So here expectation of xi is equal to mu I, where the I is between 1 and p. And then I also define the this the mu1 through mu p as the vector mu x, mu both x. And then we define the covariance matrix, which is the vectorized version of the covariance between two variables. So which is the, I say, this capital sigma is equal to expectation of the both x minus mu both x minus mu both x transpose. So expectation of the mu x, the both x minus both mu x and x both x minus mu both x transpose of the expectation of these product, this matrix product is the covariance matrix. So here, this is the, so you know that the, so this x1 through xp is the this both x is the column vector. So usually in the statistics, when we have vector, we usually express as that it's a column vector. So we have this column vector here, and then transpose column vector here, and we have matrix product. So what's the dimension of the covariance? What's the dimension of the matrix X? I mean matrix sigma. Also, everyone agree with this? The sigma, the dimension of sigma is the p by p. So here we have the p by 1. And when you take a transpose on here, then it's going to be the row vector, which is the 1 by p. So you have a p by 1 vector and a 1 by p vector, and the multiplication, the matrix multiplication will be the p by p. So the sigma ij, the ij element of sigma is the expectation of the product, two products, the product of the xi minus expectation xi, xj minus expectation xj, which is the usual covariance when we have the two variable. And then if I is equal to j, so we have usual variance. So form of the covariance matrix is the, so we have the p by p. So we have a sigma 1 1 through sigma 1 2 and sigma 1 p. So here the sigma 1 1 is the variance of the x1, and then sigma 2 is the variance of x2, and sigma p is the variance of xp. So the diagonal of a covariance matrix is the variance of each random variable, and then the off-diagonal term is the covariance between two variables in the random vector. Is this clear? Okay, so then we can also think about correlation matrix. So correlation matrix is defined by um, the which is the generalization of usual correlation. So remember, if we can define the correlation. Correlation would be the covariance divided by standard deviation of x times standard deviation of the y if you have a true variable. So here, this the diagonal term should be 1 because the diagonal term means that so we would like to find the correlation between um, two identical variable. So let's say for this, the first element, here this one is the correlation between x1 and x1. So correlation of itself, it should be correlation should be 1. And then the for off diagonal term, we can define the correlation between the two variables, which is defined as the covariance divided by product of standard deviation of x and standard deviation of the two variables. So we have properties of the covariance matrix. So the sigma is the expectation is equal to expectation of x transpose minus mu x and mu x product of matrix product of mu x and mu x transpose. And then the covariance matrix is symmetric matrix. So here, the symmetric matrix, this fact is very clear because the covariance is of if you look at the covariance between two variables, if you just interchange order of the two variables, it should be the same. So so when you change the order in the covariance between two variables, it is the same. So so covariance is exchangeable. So it's a symmetric matrix, and it's a positive definite. So mathematically speaking, is a positive semi-definite if you consider the case when the variance can be 0. But here we usually assume the variance is the strictly greater than 0. So we can think so it is the positive is definite. So the positive definite means that so if you remember the what we have reviewed in the first and first and second lecture. So the positive definite means that when you construct the quadratic form, so for any a, for any vector, uh, so this is the definition of the positive definite. Then there are many good properties of the covariance matrix. For example, the eigenvalue is positive and etc. But I think for this course, I think for properties of covariance matrix, then um, so it's a symmetric and it's positive definite, and I think that um, I mean those facts are enough to understand the materials in this course. So we have the let's look at the properties of the random vectors. So we have the x and y. These are the random vectors. I presumably assuming I am assuming that they are p by 1 vectors. That means mu both symbol x and mu both symbol y, and covariance matrix is this is capital sigma xx and capital sigma yy. And then here the a, let's say a is the n by 1 vector and b is the n, both is n by p that matrix. So then expectation a plus b times x. So here the we our matrix is the b is the m times p, and then x is the as you know, x is the p by 1. So that means that this a plus bx should be n times 1 vector, right? Is this okay? Here a is n times 1 vector, and b is the n times p matrix. So b times x is equal to is the m times 1 vector. And then the variance of a time plus bx is the b times the sigma xx is b transpose. And then expectation x plus y is the mu x plus mu y. So you can decompose the addition to make the two separate expectations in this vector case. Well, this is uh, the same property as the when you have two single random variable, and if every element x is uncorrelated with y, and the variance of x plus y is the variance x plus variance y. So here we have our vectors. So if you want to decompose the variance uh, variance of the sum of the random vectors as the two sums of the individual random variance of random vectors, then you have to have that the every element of x is uncorrelated y. So means that if you have the x1 x as the one through xp and y is equal to y1 through yp, and covariance y1 xi yj should be equal to 0 for all i's not equal to j. So this assumption is quite strong. Because it requires every element of x should be uncorrelated with y. Any questions?
Doctor,
Yes?
I have a question about the variance of the sum x plus y.
Okay.
If x is not correlated with y, it holds the usual rule for variance, like variance of x plus variance of y plus 2 covariance of x and y.
Yes. So when you have the just the usual random variables, I mean, if we allow the um, x is the correlated y, then you have the covariance of the x and y plus 2 times covariance of x and y. Yes.
Okay, thank you.
So basically, in that case, where the covariance of x and y is the cross product of the x and y. Any questions? So far, so good. if you so if you turn on the microphone, then please turn off the microphone. Okay, thank you. And so I would like to define the multivariate normal distribution. Um, so so we define the bivariate normal distribution when we have two variables, and this is the more general form of the normal distribution when we have the random vector. So this multivariate normal distribution includes the case of the bivariate normal distribution, which means that the bivariate normal distribution is the special case of the multivariate normal distribution. So we denote as the x and part of normal distribution with the mean view of the bold symbol x and the covariance the sigma, covariance matrix sigma, which has this PDF form. Um, so there are the many packages in the R to do computation on in using this multivariate normal distribution. One is the if you look at the library package, the math, then there is the function called the MVR norm. So you can use that to generate random numbers from this multivariate normal distribution, or to compute the density, or to compute the probability from the multivariate normal distribution. So here we have the we want to look at properties of a multivariate normal distribution, which means that the A, let's say A is the p by 1 vector, and then the distribution of the A transpose X is the, so if you have A transpose S, and here to make the inner product with A and doing inner product A and A transpose X, this is, what will be this A transpose X? Mean what is dimension of A transpose X? Okay, anyone else?
Never mind. I think I'm because A transpose would be a 1 by P, and then X is 1 by P.
Okay, so you think that it should be what? What's the dimension? You think the dimension is 1 by P? Okay, so we have, so A transpose is the 1 by P. And here X is P by 1. So if you do matrix product, it is 1 by 1, which is the just the single variable. So A transpose X is the linear combination of the elements in the random vector. Yes, Rao?
So X is a column vector where we have like P rows and one column.
Yes, but the A is the column vector, but the A transpose is the row vector.
Okay.
So A transpose X gives the just a single random variable, which is the linear combination of x1 through xp with the um, the sum of the products with the elements in the A. So we have, so that's the normal distribution with the A transpose mu x, which is also single number, and the variance of the variance would be A transpose sigma A, which is the also the single number. So this first property is a re-expression of this one. So I think if you remember, So if you have the x1 to xi has a mean mu I and sigma square I, so they have a different mean, different the variance, and that they are correlated. Then it's the linear combination with AI. Is the sum of the AI xi is the normal distributed with the sum of the AI mu I with the variance the a square variance AI square times variance xi, and then sum of that, then 2 times the sum of the covariances. Sorry, 2 times AI AJ. There should be AI and AJ here. So this the matrix version. So this is the this first item is the re-expression of this result in the matrix form. And then let's say A is the m times 1 vector and P is the m times P matrix. And then the distribution of A plus Bx is a normal distribution with A, there should be no transpose in here. Oops. There should be no transpose. A plus B times mu x plus the B times sigma B transpose. So as we saw before, we know that this A plus Bx has a mean A plus B times mu x, and then variance the B times sigma B transpose. But the linear combination of normal distribution preserves the the normality in this case, which is a very important property in the multivariate normal distribution. And then the for different xi and xj, xi and xj are independent if and only if sigma ij is equal to 0. So for usual random variables, if they are independent, their covariance is 0. But the other direction, the covariance is equal to 0, does not imply that they are independent in general random variables. But if these we have a multivariate normal distribution, independence is equal statement with the covariance is equal to 0. And also, pairwise independence of xi and xj also implies a mutual independence. This is also a very important result because usually mutual independence does not imply pairwise independence. But For multivariate normal distribution case, if you have multivariate normal random variables and their pairwise independence is equal to the mutual independence. So this multivariate normal random variable has very good properties. So that's one of the reasons why people use the normal random variable in the practice. Any questions?
Yes, doctor. What's the difference between pairwise and mutual independence?
Sorry?
What's the difference between pairwise and mutual independence?
So pairwise independence means that so if you have a normal density on here, um, if you have any pairwise independence is if you have the joint distribution x and xj for any pair. So let's say x1, x1, x2, x1, x3, or x1. So if you have a three, let's say if you have a three variables, okay, x1, x2, x3. So here the pairwise independence means that x1, joint distribution of x1 and x2 is equal to x1 and x1, partial distribution of x1 times partial distribution of x2. And so you can make and you can that holds for the any pair. So for example, if you have x1, x3 pairwise independent means that so you can make a joint distribution of any pair. If that's the case, if that they are equal to product of individual marginal distributions. Pair in the individual in the pairs, product of individual marginal distribution in the pairs, then we say that it's a pairwise independence. Is it okay, Dennis? Everyone okay? Yes?
Dr. Cho, this question might seem a little bit unrelated, but if we're learning about multivariate normal distribution right now, then what are we gonna? Then what's the purpose of the next semester, which is multivariate data analysis?
So for here, I'm talking about multivariate normal distribution because of the partial correlation. So we are not going to talk about more about many things about multivariate analysis. So multivariate analysis is the case that when we have the multiple responses and with the multiple predictors. So in this course, we only talk about a single response and multiple predictors. But for the partial correlation, we generally assume that the multivariate normal distribution. So that's I'm just mentioning because of that.
Okay, thank you.
Okay, so coming back to the Dennis's questions. So mutual independence is in our case so mutual independence means that if you make any pair or whatever point distribution that you have, then you always have means that the always have that your joint distribution is decomposed into the marginal product of the marginal distribution. So that's the mutual independence. So mutual independence is stronger than pairwise independence. So mutual independence implies that pairwise independence, but pairwise independence does not imply mutual independence in usual uh, random variables. But for this multivariate normal distribution, they are the same. Okay, so this is the three-dimensional picture for the density function of the bivariate normal case. So, so this x and y, we have a x and y on here, and then this we have the bell-shaped. I mean, the structure for the density on here. So if you only look at this one, so if you ignore this y and only look at this x part, we have the bell-shaped curve, which is the usual univariate normal distribution. And then if you look at this y part, ignoring x part, then you can also see the bell-shaped curve, which is the univariate normal distribution. So this is the 3D plot of the bivariate normal distribution. distribution. For the multivariate, it is very difficult to visualize because we have a limit in the three dimension. We are living in the three-dimensional world, so it is very difficult to visualize when you have the more than you have the more dimensions. But this is the basic idea. So suppose that we have a three variables, and then, like I said, if we only talk about the three variables because the more than three is very complicated. It's not very practicing usual, and also only it is only sufficient to look at this three-dimensional case to think about the partial correlation. So we are only talking about the three variables. So let's say we have this x and y and z. They have the multivariate normal distribution. That we define the correlation, special correlation. So rho xy dot and z, which is rho xy minus rho xz times rho xy minus the product of rho xg and rho yz is square root of 1 minus the correlation between square of correlation between x xz times square root of the 1 minus the correlation square of the correlation between y and z, where the rho and a and b is the marginal correlation, or you can just think of the simple correlation between a and b. So this rho xy is the correlation between x and y, rho xt is the correlation between x and z, and rho yz is the correlation between y and z. So the simple correlation. So this quantity is called partial correlation between x and y given z. So the appropriate name might be the conditional correlation. Means that we are looking at the correlation between x and y by controlling effect of the z, or conditioning on the z. So this rho, the x y times z is also the population quantity. This is the parameter. As we talked before, for rho xy, rho xt, and rho y, they are also the parameters. So this is the partial correlation. So some important facts are, so if you look at this partial correlation between x and y, given z does not depend on the z. So we are thinking that this z is given, and we only think about the partial correlation x and y. And under the multivariate normal distribution or model, the correlation between any variables given a third is the same for all values in a third, which means that there is no interaction between with the z on here. And then so this is the one aspect of this called homoscedastic property of the multivariate normal distribution. So the partial correlation of x and y given z does not depend on z, so it does not depend on the value on the z. And then rho xy dot z, so partial correlation x and y given z is equal to rho xy if partial correlation of the simple correlation between x and z and y and z are equal to 0. So the simple correlation and partial correlation are equal if the conditioning variable independent of both of variables of interest, which means that the having information about the z does not affect the simple correlation of x and y with z, which means that the xz is the xg and y and z, they are x and z, they are uncorrelated, and y and z, they are uncorrelated. And in this multivariate normal distribution case, that's the case for x and z are independent and y and z are independent. And then the partial correlation is equal to 0 if we have the simple correlation between x and y is equal to product of the two simple correlations, correlation between x and z and correlation between y and z. Which means that when the relation between x and y is fully explained by z. So that's the same as the rho xy dot z is the partial correlation is equal to 0. Then the simple correlation x and y is the equal to product of a simple correlation with the third variable. So your correlation between x and y is explained by the correlation between uh, the product of the third variable. Any questions before we move on? Okay, so we look at the simple correlation and the partial correlations. So there is a difference between the simple correlation and partial correlation. So simple correlation. So if we have when we have simple and partial correlations, they do not go to the same direction, which means that the partial correlation may be larger or the smaller than the simple correlation, or even they have a different sign. So if you have the categorical variables, this phenomenon is called the Simpson's paradox. So this discrepancies between simple and partial correlation, that's the continuous variable version of the Simpson's paradox. So let's look at this example. So we have a score on the math achievement test, and the number of alcoholic beverages consumed in the last 30 days. And the new sample from the American middle and high school students. Then it is quite possible that correlation between these two uh, uh, are positive, is positive. Then, which means that the correlation is positive means that if you higher, let's say for example, number of alcohol beverage consumed in last 30 days, it has the then that has the same that also then in that case there is a higher tendency of the higher score in the math achievement test, or the vice versa. And then does this mean imply that the math achievement is a risk factor for the alcohol use of the students? I mean, in the common sense, it's no, right? So the opposite may be true. So higher levels math achievement are possible also with the reduced levels of alcohol use. So the reason why we have this phenomenon is we have confounder, say the grade. So if you grade in school 7 to 8 to 12, so if you look at the correlation within the grade, then we are likely to find a significant negative correlation between the X and Y, which is the math achievement test result, and I call it beverage use. However, the correlation between X and Y may be positive because both are positively correlated with grade, which means that if you have the higher grade, then your math achievement test grade may be higher. And if you have a higher grade, then your core assumption may be higher. So if you, this is the, this graph shows this phenomenon. So if you look at this, the total correlation, total case, which is this simple correlation with X and Y is positive. But if you look at the correlation within the grade 7, grade 8, grade 9, grade 10, 11, 12, they are negative. So this is the one example that we have a discrepancy between the partial and simple correlation. Any questions? So we can do inference for partial correlation as we did in the simple correlation case. Um, so I will continue this in the next time. Then I will briefly talk about the exam. So the exam, the first exam will be um, um, the Saturday. Um, um, Saturday, October 3rd, from 10 a.m. to Sunday, October 4th, 10 a.m. The coverage is the what we cover until next week. Fixed plan until September the 30th. And then the practice exam will be posted in the next week. And I may, if you want, I may go over practice exam on Thursday's office hour, next Thursday's office hour. And there give me one more homework on this Friday, which is due on next Friday, so Tuesday. There will be one more homework on this Friday, which is due on next Friday, and that also covers materials related to the exam. And then this exam submission is straight, which means that you need to submit exam on time. Otherwise, you get please um, submit exam on time. So I said it's at 10 a.m. on the October 4th. So the exam will be available on October 3rd, 10 a.m. So if you do not submit exam on time, then you will get the 0 grade for the first exam.
Dr. Cho,
Yes.
is it possible to, because we are the due date for the last homework is a day before the exam, so will be we receiving the solutions for the homework exam once we turn it in?
Yes. When you turn it in, then you can the homework solution will be available. Yes.
All right. Thank you.
Yeah. And then there are not many problems in the homework 3, so um, so it's not going to be too burden to you. Any questions? Okay, have a good rest of the week, and then I will meet you on next Monday.